Hello friends, in this video we are going to study about the maximum mode of working of 8086 microprocessor. So let us start with our topic. The 8086 microprocessor, it can work in two modes. One is the maximum mode and the other is the minimum mode. The difference between the two modes is that in the minimum mode, the 8086 microprocessor, it is the only microprocessor in the system, and this 8086, it is going to provide all the control signals to the other devices which are present in the system. Whereas in the maximum mode, there are more than one microprocessor, like there can be other processors also in the system, and the 8086 microprocessor, it does not derive the control signals. The control signals, they are provided by other device which is known as the bus controller. So in this video, we will study about the maximum mode of the 8086 system. Now in 8086 microprocessor, we have a pin which is known as MN/MX pin. This pin is used to select the mode. MN is for minimum and MX is for maximum. So to select the minimum and maximum mode, we have this pin available on the IC of 8086 microprocessor. Now when this pin, it is strapped at ground, means when this pin is at logic 0, then the 8086 microprocessor, it operates in the maximum mode. So we can select this maximum mode by strapping the MN/MX pin to ground. By providing logic 0 at this pin, we can select the maximum mode. In this mode, because there can be more than one processor in the system, so the 8086 processor, it is going to derive the status signal S2, S1 and S0. So 8086, it is going to provide only these status signals, only these three status signals. There is another chip which is called the bus controller, and this chip will derive the control signals. So here there is not a single processor is there. We have 8086 plus we have different processors, like we have a bus controller which is going to derive the control signals using the status information which is provided by the 8086. So 8086, it is not directly providing the control signals like in the minimum mode, whereas here indirectly the control signals are generated. They are by the bus controller, and using the status information which is given by the 8086. So there is more than one microprocessor in the system in the maximum mode. Now let's come to the components which are present in this maximum mode system. Here we will have the 8086 microprocessor. We will have latches, buffers are there, transceivers are there. We have bus controller and the memory and input output devices. So these are the different components of the 8086 maximum mode interface. In this, all the components are same, just like the minimum mode. Only one difference is there, that we are having a bus controller also, which is providing the control signals. So let us see the block diagram for this maximum mode. This is the block diagram for the maximum mode interface. In this, we have the 8086 microprocessor. We have the bus controller 8288 IC. We have latches, data buffers are there, which are also the transceivers. Then we have RAM and ROM, which is the memory part. Input output devices are there. We have chip select logic also. This chip select logic is used to select the memory and the input output devices. Also, we have the clock generator here. This clock generator, it is going to provide the clock signals, the timing and the control signals to the 8086 processor. Now you can see here that 8086, it is providing the status signal S0, S1 and S2, and these status signals are given to the bus controller, which in thus provides the control signals, the memory and the input output control signals. Okay. So let us study the function of all these components one by one. Here the bus controller IC number is 8288, and this bus controller, it derives the control signal. Like read and write for memory and input output devices. Also the data enable, data transmit and receive, ALE. All these signals are derived by this bus controller using the status information. Okay, so in the block diagram you can see this was our bus controller. It is having the input S0, S1 and S2. Also it is having the clock input here. So it is providing the memory and the input output read and write signals. Also it is providing the interrupt signals, INTA, acknowledge. This data transmit and receive, data enable, address latch enable, ALE. So all the signals which are first given by 8086, they are now given by this bus controller. So if we talk about the input to this bus controller, then input signals will be S0, S1, S2 and the clock input. And if we talk about the output, it is going to provide the memory read or memory write, input output read, input output write, means it is going to provide MRDC, MWTC, IORC, and IOWC. These are the input output and memory read and write operations. Also it is going to provide the control signals like DEN, data enable, the ALE, also the data transmit and receive. Then it is going to provide the interrupt signal also, INTA. Okay. So these are some of the input and output signals of this bus controller. Also, it has signals like AMWC and AIOWC. These are the advanced memory write and input output write operations signals. We can say these are the advanced memory and input output write signals. The output signals like AEN, IOB and CEN. These are the pins of the bus controller 8288. These pins are used for multiprocessor systems. These signals we are going to study in detail when we will study the maximum mode interface. There we are going to study about these signals. Out of these signals, AEN and IOB, they are generally grounded, and CEN, it is connected to the plus 5 volts. Okay. Now these signals, these are provided by the bus controller. Okay. Now in this you can see that IORC and IOWC, these are for the input output operation, and MRDC and MWTC, these are for the memory operations. Now when in this block diagram we have input output devices also. So when these input output devices, they are communicating with the microprocessor, then bus controller, it is going to use these signals IORC and IOWC to read or write data from or into the input output port. Here you can see that input output port is here. We are having the read signal connected with IORC and write signal connected with IOWC. So this is for the input output. Here we have the memory. So for memory read and write, because we have two types of memory, RAM and ROM. So this random access memory, it can be read and write also. So we have both the signals here. The ROM, that is the read only memory, it can only be read, no write operation is associated with it. So the read signal is connected with MRDC only, no write signal is here. For this we have MRDC and MWTC, that is memory read and write for RAM. Okay. Then this chip select logic, it is providing the chip select signals for the RAM, ROM and for the input output. And these chip select signals are given here, CS0, CSE, CS0, CSE. These are given by the chip select logic. This is using the A0 signal, the A0 address line of the 8086 microprocessor. We have latches here. These latches are used to separate the address and data, because in 8086 we have multiplexed address and data bus. So both this bus is used as both address bus and data bus. So to separate the data from the address, we have these latches. Here we have the address which will be provided, which is used to select the memory or the input output devices, and the data will be given to the data buffers. So that data can be written into the memory or to the input output devices. So we have these internal buses, internal data bus, which is writing or reading the data from the memory or input output devices. Now these latches, they will get the control signals from the bus controller. Like address latch enable will be used to separate the address and data. Then data enable, it is used to enable the data buffers. Okay, data transmit and receive, this is used to decide that whether is the direction or flow of data, that whether the data is going to be transmit or received by the microprocessor. Okay, so here I have described all the signals in some short details. Like here we have the reset signal, clock generator, which is generating the clock using the crystal connected here. Then we have reset signal to reset the condition to clear out or to bring the microprocessor to its initial conditions. We have ready. This signal is used by 8086 to introduce the wait states when the peripheral devices are communicating with it. Okay, so this was a short description of the block diagram of the maximum mode of 8086 system. Now let us come to the timing diagram of the various machine cycles of the maximum mode. So timing diagrams for the various machine cycles, like we will have memory read, memory write, input output read or input output write machine cycles. We have opcode fetch machine cycle also here. So here in this video we are going to study the two machine cycles, the memory read and memory write machine cycles. First, we will start with the memory read machine cycle. Now, when we have studied about the minimum mode of the 8086 system, we studied that the difference between these two modes is that in minimum mode, the control signals are provided by the microprocessor, whereas in the maximum mode, the control signals are provided by the bus controller. So in the when we will study the timing diagrams for the machine cycles, here the difference will be for the control signals. So let's see the timing diagram for the memory read and memory write cycle. So a machine cycle, it consists of various T states. So at the beginning of the bus cycle, the A0, S1 and S2 signals, they are set at the beginning of the bus cycle. Then as all the control signals, they are provided by the bus controller. So the control signal ALE and the data transmission and receive signal, they will be given by the bus controller at the start of the bus cycle, means during the T1 T stage. So if we see the timing diagram for the memory read machine cycle, this is the timing diagram. Here the full one bus cycle, it consists of T1 to T4. Okay, it is the clock pulse. Okay, then we have the ALE signals, that is the address latch enable. So at the start of the bus cycle, means during the T1 T state, this ALE signal is high, and also the S0 means the S1 and S2 status signals and the A0 that is the address signal, all will be set by the bus controller at the beginning of the bus cycle. Also, this data transmission and receive signal, because here this is the timing diagram for the memory read machine cycle. So data has to be read by the microprocessor. So in this case, the receive signal is low. Okay, so receive signal is given, and this is a memory read machine cycle. So memory MRDC, this signal will be low during the complete cycle. So these signals indicate that it is the memory operation, and also read operation has to be performed. ALE signal is high. So at this time, the address and the data bus will be carrying the address, that is A0 to A15, and this address and status bus, that is A16 to A19, it will be carry the higher order address. So complete address is available when this ALE signal is high, that is during the T1 T state. Now when this ALE signal is low, then after this, during the T3 and T4 T state, we have data available here. Okay, so at this memory location we have this data. So this data is going to be read by the microprocessor. This will be the address of the memory location, and this will be the data. So when data is available on this bus, at the same time status signals will be available on the A16 to A19 address bus. This will act as the status signals, and this is going to act as the data bus. So this is our data. These are our status signals. S0, S1 and S2, they have become inactive during this period. After T4, they again become active. Okay. During this time, only the status signal S3 to S7 are available. S3 and S4 we can use to select the segment address, and S5 is for the interrupt enable, and S6 is always kept at logic 0. So here the segment from where the data has to be read, that can be selected. Okay, so this is the, here also we have the data enable signal. So when data is available, this, when this data enable signal is high, then only this data will be made available to the microprocessor. You can see in the timing diagram that in the T2 T state, this data enabled signal that is enabled. You can see here we have the T2 T state, and this is made high. So this signal, it is going to enable the transceivers. Now these transceivers, they can transmit and receive the data also. So this is going to decide that whether the data is going to be transmit or received by the microprocessor. So if we have for the input, it is going to activate the MRDC or IORC. Means if we are having the input, we are receiving the data, then the memory read and the input output read signals, they will be activated. If it is for output, means data is going to be transmit, then it is going to activate MWRC, WTC or IOWC. So this will be the read operation, and this will be the write operation. Data will be received, and here data will be transmit. So this bus controller will decide that when this signal data enable is 1, then transceivers are enabled. At that time, this data which is available on the data bus, that will be received by the microprocessor. Okay. Now when we study the case of memory write machine cycle, so in memory write machine cycle, this is the timing diagram for it. We have the clock cycle, clock pulse here. Again, ALE signal is high. So when ALE is high, we have the address available on the address bus, and Here also we have the address, that is A19 and to A16 is available. When this signal is low, then we have the status signal and the data. Now this data, because it is a memory write machine cycle, so data will be written at some memory location. So this data which is available, that will be written at the memory location which is addressed by this address given at the available at the address bus. Then we have these AMWC or AIOWC. These are the advanced input, output and memory write operations. So when these signals are low, then write operation will be performed. Also, we have the memory write and input, output write signals also. So they will also be low at this time. This data transmit and receive, because data is going to be transmit to some output port or memory location, so this has to be high. So this signal is high during the complete cycle. Also this data enable signal, this is low, so it is going to enable the transceivers and it is going to enable this data transmit and receive signal also. So this is for memory write machine cycle and this is for memory read machine cycle. The difference is that of the control signals, like these memory write and memory read operations are different. Okay, if it would be input output read or input output write, then here we will have the input output operations available. Data transmit and receive, it is different. In the case of memory read, it is low. In the case of memory write, it is high. Okay, that is the difference between the two cycles. So here I have written that in the T2 T state, this bus controller, it is going to set the data enable signal. So you can see here that these signals, the memory read and the input output signals, they are activated till the T4 T state. They will get activated during this T2 T state and they will be activated until this T4 T state. Now we have the status signal S0 to S2. These signals in both the cycles, memory read and memory write, you can see that these signals are active till the T2 T state. T3 and T4, they are inactive. In this T4, they again become active. In memory write also you can see same thing is there. They are active till the middle of this T2. In the T3 T state, they are inactive. In T4, they again become active. So here I have written the status bit, they remain active until T3 and become passive during T4 and T2. This is until T2 they are active and they become passive during T3 and T4. Now if we have the memory read or the input output read cycle, then we have to activate the read signal. So to activate this read signal, it has to be activated before the T3 T state. If we see the memory read machine cycle, here the memory read signal that is activated before the T3 T state. You can see that in the T3 T state it is active. If it is not active in the T3 T state, then a wait state will be inserted between T3 and T4. So here we will have another T state which is called the wait state. That is introduced because it means that the data which we want to read, which is available at the input output device or the memory, so the peripheral devices, they are not ready and the microprocessor processing is very fast. So to introduce some time delay, the wait state is inserted between two T states. So here if read cycle is not activated before the T3 T state, so a wait state will be introduced so that the time will be available to activate this read signal. Okay. So these are the two machine cycles, memory read and memory write. Their timing diagrams we studied in the maximum mode. Now let's come to the request and the grant signals which are available in the maximum mode. These request and grant signals, they are used by the other controllers to request the control of the buses of the 8086 microprocessor. So how these signals are generated, let's see. So the request and the grant signals, their timing diagrams is shown in this figure. We have the clock pulse here, and according to this clock pulse, we will have the request and the grant signals issued by the microprocessor. Okay. So these request and the grant signals, they consist of a series of 3 pulses. These signals are checked at each rising edge of the clock pulse. This is called the rising edge. Okay, so at each rising pulse, these request and grant signals, they will be checked by the microprocessor. If these signals are found that this request and grant signal has been issued, then here another master request bus access. So request signal will be given by another peripheral device. That device will request the control of buses. It will send a request to the microprocessor that I want the control of the buses. So if this at the rising pulse, if this request is given by the device to the microprocessor, so at the trailing edge of the next clock pulse, this is called the trailing edge. At this trailing edge, the grant will be given to the controller, to the master, that the buses are now your control. CPU has released the control and now the buses are under the control of the other processor. So here the request signal is given. Request is sent by another master which wants the control, which want to access the bus. Here grant signal is issued. So CPU grants the control of the bus to the master which is requesting the control, and here the master releases the control that now I don't want the control of the buses. The CPU can now regain the control. So here again bus control is regained. So if we describe this whole process, this request and grant signal, it will consist of 3 pulses. First will be for the request, because these are active low signals. So here we are having a low pulse. Okay, grant is also low and request is also a low signal. So it will consist of 3 pulses. First will be request, then the grant, and then the master releases the control of the bus. So when a request signal is detected and if the hold condition is satisfied, means if the hold signal is also 1, then the processor is going to issue a grant pulse during the T4, means if the current instruction is executed, so the T4 T state of the current instruction or the T1 T state of the next instruction, during that period the grant pulse will be issued. Pulse, it accepts the control of the buses and it is going to send a release pulse to the processor. Okay, so this is how the request and the grant signals they are generated in the maximum mode of the 8086 microprocessor. Now let us come to the maximum mode interface, that when the 8086 it is operating in the maximum mode, then the other devices which are available in the system, how 8086 is communicating with those devices. Okay. Now, when the 8086 microprocessor it is working in the maximum mode, so in this mode there is not one processor is there. There are many processors available. So each processor it will execute its own program. It will have its program. It will have its own control signals. So each processor it is going to work independently, and the 8086 it will provide the signals for implementing this multiprocessor configuration. Now, because in this multiprocessor configuration, there will be many processors connected. So, the resources of the system, if the resources are common to all the processors, then those resources are called the global resources. Means they can be used by all the processors connected in the system. So, those resources will be called global, and some resources they are assigned to specific processors only. They can be used by some specific microprocessors. So those resources will be called local resources, and each processor it is executing its own program. So processor can use global resources also, and it can use its own private resources, local resources also. Now, because there are many processors, so every processor will be called a co-processor. Means suppose two processors are working at a time, so one will be, both will be co-processors of each other. And these two processors, they does not access the bus at the same time. If there are two or more processors in the system, and there we are having the address and the data buses, system buses are there. So those system buses cannot be used by two processors at the same time. Only one master will be there, other will be the slave in the slave processors in the system. Those slave processors, they are going to ask for the bus control to the master processor. Okay. Now here in maximum mode, we were having different processors, and each processor is having a resource for it, like global resources are also there and private resources are also there. So 8086, this microprocessor, it is going to provide facilities to implement this multiprocessor configuration, and also to allocate the resources to all the processor that will also be provided by the 8086 microprocessor, and also the bus control, that which processor will have the bus control, that will also be decided by the 8086 microprocessor. Now, in the maximum mode, we studied that in this mode, the control signals, they are not provided by the 8086. 8086 only provide the status signals. These status signals will be given to a bus controller, and the bus controller, it is going to provide the control signals to all the other processors. So in this maximum mode, control signals are provided by the bus controller. So now let us study the maximum mode interface. Interface means the communication between the two components. So here we have the bus controller and the 8086 microprocessor. So let's see that how the microprocessor give the status signals to the bus controller, and how the bus controller, it generates the control signals. Okay. Now the bus controller IC is 8288. This bus controller, it is going to generate the bus command and control signals. So the function of this bus controller, the function of this bus controller is to generate the signals which are required to control the memory, input, output, and interrupt interfaces. So microprocessor, it will either communicate with the memory or the input output device and the peripheral devices or the interrupt devices. So these all the kinds of interfaces which the microprocessor is making, those interfaces are controlled by this bus controller. Now let's see the block diagram of the microprocessor in the maximum mode. This is the block diagram. Here we have the 8086 microprocessor, and these are the bus controller 8288 and also 8289. These are the two ICs which can be used as the bus controller. Now this bus controller 8288, it is having the three inputs S0, S1 and S2, the three status signals from the microprocessor 8086. This is 8086. Here we have S0, S1 and S2. These three status signals are given to the bus controller. Also the clock pulse, that is also an input to this bus controller. Now this bus controller, it is going to generate the control signals for memory, for input output, and for the interrupt. So for memory, we have memory read and memory write. So MRDC and MWTC, these are the memory read and write signals. Then for input output, it has IORC and IOWC, input output read and write signals. Then these AIOWC and AMWC, these are the advanced memory write and input output write signals. Then for interrupt, it has INTA signal, that is the interrupt acknowledge signal, that will also be generated by the bus controller. Then also the control signals like data enable, data transmission and receive, address latch enable, they are also generated by the bus controller. Now here we have the address and the data bus of the microprocessor. We have the bus high enable, read, ready and the queue status signals. So let us study the function of these signals and how they are generated by the bus controller using the status information given by the microprocessor. Now in control signals, we have the signals like ALE, input output and memory signals, data enable, data transmission and receive, and INTA. All are generated by the bus controller. Now let's see that the status information S0, S1 and S2, how it can be used to decide that which memory or input output operation will be performed by the microprocessor. We have S2, S1 and S0. We have three signals, so these three signals can have 8 combinations: 0, 0, 0. So here we are having the 8 combinations, and this is the bus controller command. Which command will be generated by the bus controller? Let's see. If it is 0, 0, 0, then INTA signal, which is an active low signal, that will be generated by the 8288. And this signal, it is for the interrupt acknowledgement, that when an interrupt request is received by the microprocessor, in response to that it will give the acknowledgement signal INTA. Okay. Now when it is 001, then IORC, input output read command will be generated, and this will also be an active low signal. If it is 010, then input output write or the advanced input output write command will be generated. If it is 011, then no command is generated, none. Then when it is 100, then MRDC, that is memory read. If it is 101, then also it is MRDC. It will be the instruction fetch, or we can say opcode fetch, and MRDC, it will be the memory read. If it is 110, and these are the memory write and the advanced memory write and memory write operations. So here we will have memory write. Then 111, there will be no operation, that is none. So if these are the commands that will be issued by the bus controller. If we write here that what this describes, 000, what's the interrupt acknowledgement? It's an interrupt command. Then we were having input output read, input output write. If it is 011, none means halt condition is there. MRDC was instruction fetch or opcode fetch. MRDC it was memory read, then memory write, and none it is for the passive. So here you can see that the status information which was given by the microprocessor 8086, that status information is used by the bus controller 8288 to generate the control signals, to give the commands to the uh, processors, like when it is communicating with the interrupts, then it has interrupt commands. Then with, if it is interfacing with the memory, then memory signals are there, and if it is interfacing with input output devices, then also it has input output signals. So these commands will be issued by the bus controller depending upon the status signals given by the microprocessor. Also this bus controller, it is also generating the signals, the data transmission and receive. So this is for data transmit or receive. Then we have ALE, address latch enable. We have DEN, the data enable. The function of these signals is same as in the case of the 8086 microprocessor. This signal, if it is high, then data is going to be transmit. If it is low, then the data is going to be received by the processor. Address latch enable, if this signal is high, then address will be available. If this signal is low, then data will be available on the bus. Then we have data enable. This signal, it is going to be, if it is low, then it is going to enable the transceivers. Transceivers are used to transmit or receive the data. So this signal is going to decide the direction of flow of data. So these signals are also generated by the bus controller. Okay. Now we have the second bus controller, that is 8289. Here you can see in the block diagram of the maximum mode, 8289 bus controller, it is also having the three status signals as the input, and also we have a input, clock input is there. Then it is generating the signal INT, that is interrupt, and also these signals are also generated by it. Now what's the function of these signals? Let us see that how these signals are generated and what are their functions. So this bus controller 8289, it is going to generate the signals, bus arbitration signals. Okay, like we have bus busy, so we have the busy signal. Then CREQ, the common bus request. BPRO for the bus priority out, and bus priority in is BPRN. Then bus request and bus clock signals. You can see in the block diagram that this bus controller, it is generating these bus arbitration signals. Now what is the function? Bus busy means that the system bus is at the present time it is busy, and when it will be free, it will be issued to the other processors. Now these processors, because we have studied in the starting in the maximum mode that there are several processors, and each processor wants the control of the system buses, of the buses of 8086. So how this buses will be issued, how these requests will be granted, that will be decided by the 8289. Then we have a common bus request on this, when all the processors they are sending a common bus request. Bus priority out and bus priority in. Suppose two processors they are sending the request to the microprocessor at the same time. So how the priority is decided among the processor, that will be decided by the two signals, bus priority out and bus priority in. Then bus request will be given by the processors to the bus controller, and bus clock, it is the clock input. Okay. Now when the 8086 microprocessor it is executing an instruction, and at that time it receives a bus request, then if the processor 8086 it want to lock the system buses, that for this instruction no processor will be able to get the control of the buses, then it sends a signal which is called lock. Okay, so this instruction lock, this signal, it locks other processor of the system's bus, means they are not going to get the control of the system buses during the execution of an instruction by the 8086. Now the when this lock signal will be given, then this lock signal ensures that the microprocessor it is going to perform an uninterrupted process, because no other processor will be able to interrupt it, will be able to get the control of the buses. Now in the block diagram also you can see we have the lock signal. This lock signal will be given by the microprocessor to the bus controller. So other processors they will not be able to get the control of the buses if its lock signal is activated. Also this interrupt is the signal generated by the bus controller. So this was the interrupt signal that is generated by the 8289 to interrupt the microprocessor. Now here you can also see that microprocessor is generating two signals, QS1 and QS0 also. These signals are the Q status signals. So let us study about these signals. So we have the two Q status signals, QS1 and QS0. Now we know that the 8086 microprocessor it executes the instructions in the form of queue, means it prefetches six instructions, and these six instructions opcode will form a queue, and one by one they will be executed. So this queue formation it helps in fast processing or fast execution of the program. So let's see that how these Q status signals, the combination of the two signals, what these combinations describe. So when these two signals they are 0 0, it means that the queue is empty. The queue that is formed where the opcodes of the instructions are stored, that queue is empty, and that is empty because the queue has been reinitiated due to the execution or due to the transfer of an instruction. So if the instruction has been transmitted or if the queue is empty, then 0 0 are the queue status signals. When it is 0 1 means first byte. Now when the queue status signals they are 0 1, it means first byte, means the byte which has been taken from the queue, that is the first byte of the data. Then if it is 1 0, again the queue is empty, means queue has been reinitiated as a result of the execution of a transfer instruction. Then QS1, QS0, if it is 1, 1, then it means that subsequent byte, means the byte which has been taken from the queue, that is the subsequent byte of the data. So in this way, these queue status signals, they describe the status of the queue in which the opcodes of the instructions are stored. So together these two queue status signals, they are going to form a 2-bit code QS1, QS0, and this code is going to decide the status of the queue. Also the bus controller 8289, it generates the local bus control signals. Like the request and the grant signals. Okay, so these local bus control signals are the request and the grant signals like hold and HLDA. They will be granted in the case when DMA controller is present here. Okay, so these will also be generated by the bus controller. So let's us again come to the block diagram of the 8086 in the maximum mode. We were having the 8288 bus controller which was generating the memory and the input output control signals and the interrupt control signals, whereas the 8289 bus controller, it was generating the bus arbitration signals, like to state that whether the bus request is given or bus is busy, or a common bus request, bus clock signals. So these are the bus arbitration signals. Also we have the lock signal here and the signals like the request and the grant signals. So when the 8086 microprocessor, it is working in the maximum mode, all the control signals will be generated by these two bus controllers. So in this video, we studied about the maximum mode of the 8086 microprocessor. In this, we studied that how the 8086 it works, what are the timing diagrams of the various machine cycles. Then we studied how the request and the grant signals they are issued. Then we studied the bus controller which provides all the control signals. So that was the block diagram in the maximum mode of the 8086. So I hope that this topic is now clear to you. Thank you.